All right, so the three equations on the beginning of your equation sheet, or sorry, your reference sheet, are uniformly accelerated motion, where acceleration is constant. So I wanted to show you sort of where those equations come from. And I guess first I'll do a motion map showing constant acceleration. This is a simple version of constant acceleration where you're just simply speeding up. So your acceleration is causing you to speed up. In other words, it's causing your velocity vectors to get longer. So your motion map might look like that. In words, a description would be object starts, I'll make it simple. I'll say it starts from rest. Problems like to say that. People like to say that a lot. And uniformly accelerates. Now, accelerates does not mean speeds up. Some people use it in that context, but in physics, acceleration can mean you're speeding up or slowing down. In this case, you happen to be speeding up while moving in the positive direction. Okay, so those words would be a description of this motion on the motion map, and I'll make a little plus here to show that's positive direction. This is a negative direction. Okay, so that's a start. We'll do some graphs now. I'll draw a position time graph first, then a velocity time graph. So I'll make a nice stack of graphs, and then an acceleration versus time graph. And I'm primarily just concerned with the shape of these graphs right now. This is an X. Okay, so our slope would need to get steeper and steeper, something like this curve, right? Sort of like that. Slope gets steeper and steeper as time goes on. That's a little slappy. There we go. And if I start from rest, that makes it easier because I start right at zero velocity and speed up while moving in the positive direction. So you can see the velocity is, the numbers that correspond to the velocity would be getting larger at a steady rate. That's what we mean by uniform acceleration. Let me straighten that line a little bit. See if that looks better. There's a little better. Okay, so our acceleration is constant. See, this implies constant acceleration, motion. Constant acceleration. That's just another way of saying what that graph means. And we also say the words uniform acceleration. That's why these equations that I'm showing you are called UAM equations. Okay, let's just look at the areas of the graphs and translate our graphs into vector equations. If I take the area of this graph, that's a nice simple one to start with, right? So area of A versus T graph, you'll recall that is equal to a change in velocity, right? Which is given the symbol delta change V with a vector symbol to show its velocity. V without a vector symbol actually represents speed. So change in V, so that's going to be equal to the area of that rectangle, which is acceleration times time. And change in V, change in velocity vector, would be your final velocity minus your beginning velocity. And this, I'm talking about vectors here, so subtracting vectors. And acceleration, of course, is also a vector. Okay, so another way we can well, let's go up to our velocity graph. That'll be easier. Okay. Now, if I take this relationship here and look at my velocity graph, this in the beginning is my initial velocity. It looks like in this case my initial velocity is 0, but that's my initial velocity. And then at final time t, this would be my final velocity, right? And this is just at time t that we decide. So this amount from there to there is going to be AT, since that's V final minus V initial. And these are vector quantities, all of them, but on a graph you can only show positive and negative direction of a vector. So graphs are limited in that way. You'd have to have a series of graphs for every axis, like one for the x-axis, one for the y-axis, one for the z-axis, to do this in 3 dimensions. Anyhow, here is the area of your velocity graph, right? And you probably recall that area of velocity graph is going to be a triangle, right? So it's going to be 1/2, and then AT, right? And then I got to multiply by the base, t, right? And that simplifies to just 1/2 AT squared. So that's when your initial velocity is 0, right? So that's when V naught, initial velocity, is 0. Things are a lot simpler then. And so what I'm saying is area of velocity graph is actually displacement, and it's given the symbol triangle x, or change in position. And again, the fancy word for that is displacement. Change in velocity doesn't have like a fancy word. We can also look at the slopes, okay? And I'll do that up here. So average velocity is going to be the change in position divided by change in time, right? And that's going to be the slope of a position versus time graph. Now, that's different from instantaneous velocity, which you would need in this case, because your position graph is not a line. So I'll say this is when linear. When you have a curved position time graph, as you do in this case, you would have to do something called taking the limit. Now, this is a calculus term, but I'll just write it out first and then explain. You're taking the limit as your 2 moments in time get closer and closer together. That is, the change in time is approaching 0. And you're doing the same thing. You're taking the slope of your position time graph, but since it's a curve, you can't really take the slope of the curve. You have to take the slope of tangent lines. That's all this means. These are fancy symbols that mean slope of tangent lines. So slope of line tangent to curve on position versus time graph. And this is when your position time graph is curved. Okay? And I should probably say that acceleration is change in velocity divided by change in time. I'll write that over here. Acceleration is change in velocity divided by change in time. Okay? And that is the slope of velocity versus time graph. Oops, don't want to do that. Okay, so that's just a basic introduction, and then the first equation on your equation sheet, on your reference sheet, is the equation of this line. That's one way of getting it. So I'll show you that on the next slide.